Welcome back. During the preceding sessions, we completed the diagnostic journey. Now we start on the remedial journey from cause to remedy. This journey involves several phases: choice of alternatives, remedial action, dealing with resistance to change, and finally, establishing controls to hold the gains. A diagnostic journey may turn up any of a wide variety of causes. For example, product design weakness, or process design weakness, or instrument not precise enough, or worker lacking technique. One alternative for remedy is to remove the cause. For example, redesign the product to remedy the design weakness. But we should look at other alternatives also. Let's look at two case examples. Our first case was a company making and selling chemical intermediates. The product had limited shelf life, and there was a costly extent of goods returned from the field for reprocessing. To increase the shelf life involved risky chemical research at unpredictable cost. Instead, the company adopted date labeling of the packages to help the clients know which material to use first. Our second case involved a company making sterling silverware. There were extensive rejections at final inspection due to tiny blemishes on the product. The resulting rework was costly. To provide a remedy by re-engineering the process was also costly. The company then conducted a market research, and it discovered that many of the appearance standards were unrealistic when compared with reactions of users in the marketplace. Hence, much of the remedy was to change the visual standards. Normally, remedy requires raising costs in one department in order to create benefits elsewhere. Some cases are obvious. In the case of the shafts for the watches, the cost of the new dial gauges was trivial when compared to the cost of 12% scrap and 25 sorters. In the piston ring case, the cost of the new tools and instruments was $50,000 compared to cutting in two the $1.2 million of quality-related costs. But it is easy to be fooled if we consider only the facts of one department. Remedial action may reduce costs in that department, but increase the overall costs. The need is to optimize company costs and users' costs. We can reduce the risk of sub-optimizing by interaction among steering arm members. The choice of alternatives is helped if we quantify for all alternatives the cost impact on a company-wide basis. We should study the effect of the proposed remedies, not merely on the cost of poor quality, but also the effect on other costs. For example, material usage, facilities usage, productivity, energy consumption, and so on. It is risky to let just one department check out all these costs. It requires a team. In optimizing costs, a frequent checkpoint is perfectionism, adding cost without adding value. A case in point was the sterling silverware. There, the inspection standards were unrealistic relative to fitness for use. Some perfectionism originates with clients or government regulators. Such perfectionism raises costs for all manufacturers. The resulting added costs are then paid for by those clients or by the taxpayers. There's no competitive disadvantage for any manufacturer. It is very different if the perfectionism is self-imposed. Now, the costs of the guilty manufacturer are raised, but no one else's costs. The sterling silverware case was an example. Sometimes the advocate of perfectionism is some important manager. For example, in plastic molding of lenses for street lamps, some lenses exhibited black specks. These specks were inherent in the molding process. The lenses were clearly fit for use, since the street lamps hang 10 meters up in the air. The marketing manager agreed they were fit for use, but he insisted that the product be free of specks. His contention was that the client's incoming inspection would open up some boxes to check samples and would notice the specs. In effect, the marketing manager would increase costs without evidence that the added costs would be recovered in higher income. In such cases, the added costs should be computed and publicized so as to require the advocate to defend the proposals. In that plastic lens case, there should have been joint planning with a client to set realistic standards and avoid raising the cost of the product. In our breakthrough sequence, once the alternatives are weighed, the steering arm makes recommendations. Most recommendations are made to some line department, requesting some change in technology or method. The steering arm should follow up until action is taken, and usually all goes well. We also have several categories of remedy which are not so straightforward. These include revisions in systematic approach, the trivial many defects, the rare but critical defects, and reducing the cost of inspection. First, revisions in systematic approach. These involve changes in policies, goals, plans, organization, standards, procedures, emphasis. To illustrate these, let's look at some major phases in the product life cycle. Then, for each phase, let's identify some remedies of a systematic nature. All products follow a life cycle similar to the well-known spiral of progress. The model shows how decisions and actions early in the cycle can have adverse effects later in the cycle. Added costs, delays, waste, recalls, and so forth. A new design may later prove to be very costly to make, to test, to use, to maintain. A remedy is some form of early warning, so action can be taken to avert such disaster. A major form of such early warning is through quality assurance. This term is used here in a sense similar to that of insurance. Let's sketch this out rather briskly. Here we have the word insurance, which is defined in the dictionary. And here's the term quality assurance, QA, which is not in the dictionary. In both cases, we pay a premium. In both cases, we get protection. What differs is the kind of protection we get. In insurance, we get a large sum after the disaster. In quality assurance, we get early warning before the disaster. Several quality assurance problems arise during the design phase of the spiral. One is the need for early warning on what will be the actual use of the product compared to the intended use. The designer usually knows what is the intended use, but often the designer does not know what will be the actual use and misuse. How is the designer to find out? The designer can visit the field to learn about actual use, or the designer can secure inputs from people who do have field experience. However, if there's no positive provision to give the needed information to the designer, then the systematic approach is deficient and needs a remedy. Aside from the problem of informing the designer, there's also a policy question. Should we design based on intended use or on actual use? In most companies, this policy question has never gone to the upper management for a decision. Hence, by default, the designer must answer the question. But the matter is broader than technology. It involves legal, marketing, and financial considerations as well. It should be decided by upper management. Again, the systematic approach is deficient and needs a remedy. The second aspect of design quality assurance relates to the contrast of model shop versus production shop. When units made in the model shop pass their tests successfully, it proves that such units can be made successfully in the model shop. It does not prove that such units can be made successfully in the production shop. Those two worlds have important differences. We can provide added quality assurance by changes in the systematic approach. Send designers to spend time in the production shop to learn the realities. Establish design review by persons with wide experience in manufacture, or create separate trial lots under production shop conditions. Another aspect of design quality assurance involves variability of the numbers. Only a few units are made in the model shop. Many more will be made in the production shop, orders of magnitude greater. The problem is how to predict variability of the numerous production units from data on the few models. Let's recall the quincunx to help us out. Quincunx, please appear. Thank you. Let's make 4 units of product in this model shop. We have 2 units at 11 and 2 units at 12. Suppose that the designer assumes this range will be held on production units. Acting on this assumption, the designer then sets tolerances at this same range. Now let's use the same process to make many units of product. Notice the wider range of dispersion. Many units are out of tolerance. The need here is to establish the correct statistical relationship between small and large numbers. The alternatives include train the designer in statistical methodology, or bring in a specialist in statistical methodology to work with a designer, or scale up the data through pilot production lots. Quincunx, many thanks for your help. Note those references to training of designers in various subjects: exposure to field realities, exposure to factory realities, training in statistical methodology. These are all forms of design quality assurance, early warning systems built into the designer. For modern products, designer training should go further. Modern designs exhibit numerous features which demand early warning: high precision, unnatural environments, safety orientation, high life cycle cost, high reliability. The presence of these features has stimulated evolution of new tools for early warning. Let's look at some of these. Design review is a mandated, formal procedure for study of designs to provide early warning. The study of designs is done by various specialists, mainly from manufacture, quality, and field service. These specialists have no responsibility for designing. Their responsibility is to give early warning of uneconomic manufacture, high failure rates, poor maintainability. Designers have generally opposed the adoption of formal design review, but many companies have gone ahead in spite of this resistance. Much can be done to quantify the reliability of designs. Here's an example. The left-hand column lists the various kinds of components used in an electronic circuit. The number of each can be counted from the circuit diagram. The failure rates are estimated from prior data on laboratory tests and field performance. The totals are computed using conventional formulas for reliability. In this case, the mean time between failures works out to 1,398 hours. Fault tree analysis is a systematic analysis of product design to discover weaknesses such as safety hazards. The first step is a review of past experience to discover inherent hazards. For example, the domestic gas-fired hot water heater. The bulk of the hazards are, first, a fire breaks out. Or there's a gas explosion. Or the hot water tank bursts. Next, for each hazard, we identify those conditions which must converge to create that hazard. For example, we cannot have a gas explosion without an explosive mixture of gas, oxygen, and a source of ignition. The designer then works to eliminate or neutralize these conditions through design technology. When fault tree analysis is set out in graphic form, the result looks like a tree, hence fault tree analysis. Designers have used this concept informally for centuries. What is new is the formality. This formality means more work for the designers, but it's used by some companies to reduce the risk of overlooking something and also to simplify design review for greater quality assurance. The reverse approach is failure mode and effect analysis. For each quality characteristic in the system, we raise the question, if this were to fail, what would be the effect on the system? For complex systems, this approach is very, very costly. But it's being used in some systems, space hardware, missile systems, even some civilian systems. Next, quantified factors of safety. Designs can fail from many sources, both inside and outside the design department. One broad remedy for all sources is factor of safety. Designers have used it for centuries. Recently, we have evolved some scientific inputs to help decide how big a factor of safety to use. The approach requires that we quantify two variations. Variations in the stresses and environments to which the products will be subjected, and variation in the strength or ability of products to stand up against stresses. Variations in stress and strength can be related to each other based on establishing a minimal distance between the two averages. The minimal distance is counted off in number of sigmas. If we are able to quantify the averages and sigmas, we can compute the expected failures in parts per million, or billion, or whatever. Next, aids to designers. Many are of long standing. Manuals of design standards, lists of qualified materials and components. For more modern products, added aids have been evolved. Tables of failure rates of various components, circuits, and mechanisms. Tables of process capability for principal processes. Data on costs of various processes. Two-way communication is needed. For example, designers need feedback of product performance, both good and bad. Such feedback helps the designers prepare lists of approved materials and components. We also need communication in the reverse direction. For example, which quality characteristics are safety-oriented? In the automobile industry, designers identify the safety-oriented quality characteristics. One form uses an inverted delta. This alerts the rest of the spiral to act accordingly. Now let's turn to systematic remedies in the purchasing area. The approach to quality assurance in purchasing depends on what we buy. Note the contrast of modern products versus traditional. When we buy modern products, we buy more than the goods. We also buy services, product design, process design, manufacturing planning. The quality of these services is essential to the quality of the product we are buying. Also, these essential services are performed early in the spiral of progress. Hence, we need early warnings of any deficiency in these services. So let's look at some systematic remedies in the purchasing area. Let's start with a policy on vendor relations. In Western countries, vendor relations are largely conducted on an adversary basis. The emphasis is on short-term advantages. This policy seems quite logical as to prices and other financial terms. Most companies in the West extend the adversary policy to quality matters as well. Usually it's a mistake to do that. On quality matters, the need is for a teamwork approach, including joint planning, mutual visits, mutual technical assistance, and mutual exchange of data. In quality matters, the goal should be to treat the vendor like a department in the buyer's own company. Note that within large companies, some divisions are vendors to others. The buying divisions usually employ an adversary policy on pricing, on transfer prices, but they usually employ a teamwork policy on quality matters. The systematic remedy is to re-examine vendor relations policy on quality matters. At the same time, look to see whether this policy question was ever submitted to upper management. In many companies, upper management has never faced that question. Hence, by default, the purchasing department has set the policy. Now, as to quality assurance of the vendor's design. The usual early warning is qualification testing. The vendor submits samples to be tested in the laboratories by trained technologists. This provides useful early warning despite some limitations. Mainly, the sample should represent future production and the design will not be changed without the buyer's agreement. Qualification testing of product design does not assure that the vendor is qualified to make the product to that design under factory conditions. Qualification to manufacture requires a separate form of quality assurance. The usual form is the vendor's survey, a visit to evaluate the vendor's capability for manufacture. Vendor surveys in the West overemphasize organizational and procedural features, such as written procedures, clear definition of responsibility, data systems, and documentation. In contrast, the surveys underemphasize technological capability and employee training. This systematic unbalance should not continue. A further opportunity for systematic remedy is to optimize the cost of purchased products. The cost of purchased products should include the effect of added costs traceable to poor quality. The purchasing managers agree. The purchasing managers are also willing to use such data as inputs to their decisions on choice of vendors. But in many companies, something is lacking. Translation of the quality data into the language of money. The lack of such translation is a distinct handicap to the purchasing manager. The systematic remedy is to translate the inspection and test data on poor vendor quality into the language of the purchasing manager, the language of money. If this takes a lot of effort, then apply the Pareto principle. Just translate the vital few cases. Now the high points of Session 12. In choosing remedies, optimize company costs and users' costs, not just departmental costs. In product design, look for needed systematic remedies in areas such as design for actual use, not the intended use. translation of model shop results into production shop predictions, training of designers, adoption of design review, quantification of reliability, formalized safety analysis, provision of aids to designers, and communication both ways. Purchase of modern products includes purchase of essential services such as product design and manufacturing capability. In purchasing, look for needed systematic remedies in areas such as policy of teamwork relationship, not adversary relationship, qualification of vendor manufacturing capability by emphasis on technological and personnel capability as well as procedural capability, and evaluation of cost of purchased products by including costs of poor vendor quality. Between now and the next session, look back over prior quality improvement projects in your experience. To what extent have they examined the alternatives discussed in this session? What are your conclusions? As to your current project, examine the possibility of applying the alternatives for remedy as discussed in this session. Also, read the workbook notes for session 13. Good luck.